Have you ever thought about why autoregressive models like GPT are so powerful in generating text, but always struggle to achieve high resolution when generating images? Today, we are introducing a new technology that may change this situation, token shuffle. This technology not only enables autoregressive models to generate high-definition images at 2048 Cheng 2 2048 resolution, but also outperforms other models in performance. How does it achieve this? Let's explore this interesting technological innovation together. Before we begin, let's first understand the background. Autoregressive models have achieved great success in the field of language generation, such as the well-known GPT series. But in the field of image generation, they always seem to lag behind diffusion models. One main reason is that images require a large number of tokens to represent, which leads to inefficient training and inference, and also limits the resolution of generated images. Let's delve deeper into this issue. Imagine you want to generate a 1024 Cheng 2 1024 resolution image. In traditional autoregressive models, each pixel requires a token to represent it, which means processing over 1 million tokens. It's like writing an extremely long book, where each word must be written one after another, while also considering contextual relationships. This not only requires enormous computational resources, but also results in extremely slow training and inference speeds. This issue is mainly reflected in three aspects. First is computational complexity. Taking Transformer as an example, its computational complexity is big O of n squared, where n is the number of tokens. This means processing 1 million tokens requires approximately 1 trillion operations. Second is memory consumption, where each token needs to store its feature vector. For 1 million tokens, this may require tens of GB of memory. Finally is training efficiency. Due to the enormous number of tokens, each training step needs to process a large amount of data, resulting in significantly increased training time. So, how does Token Shuffle solve this problem? Its core idea is actually quite simple. Reduce the number of tokens by merging spatially adjacent tokens. This might sound a bit abstract, so let's use a more concrete example to illustrate. Specifically, Token Shuffle involves two key operations. The first is Token Shuffle, which is responsible for merging spatially adjacent tokens. For example, merging 4 adjacent 8 Cheng 2 8 pixel blocks into one 16 Cheng 2 16 block. This process is like playing Tetris, combining small blocks into larger shapes. During implementation, it concatenates adjacent tokens along the channel dimension, preserving spatial locality, ensuring that the merged tokens are visually related, and then maps the merged tokens to the appropriate dimension through a linear transformation. The second operation is Token Unshuffle, which, after the transformer processing is completed, unfolds these merged tokens to restore the original spatial arrangement. This is like decompressing a file, restoring the compressed data to its original form. Specifically, it will split the merged tokens back to their original size, restore the original dimensions through inverse linear transformation, and maintain the spatial structure and detail information of the image. The cleverness of this design lies in the fact that it does not require modifying the standard causal transformer architecture and can be directly applied to existing models. At the same time, it maintains image quality, as the merged tokens are spatially adjacent and have similar visual features. Moreover, it significantly improves efficiency, reducing the number of tokens that need to be processed while maintaining generation quality. More importantly, it supports dynamic adjustment of the shuffle window size, allowing for balancing efficiency and quality as needed. Let's take a look at Token Shuffle's actual performance. In the Gen AI benchmark test, a 2.7B parameter model achieved an overall score of 0.77. This result surpassed other AR models, like LlamaGen, by 0.18 points, and even exceeded the diffusion model LDM by 0.15 points. Even more impressive is that it was the first to increase the resolution of AR text-to-image generation to 2048 Cheng 2 2048. Of course, any technology has its limitations. While Token Shuffle solves the issue of token quantity, it still faces the inherent visual defects of AR models. This is mainly because the working principle of autoregressive models limits the interaction of global information. Specifically, during the generation process, the model can only see the parts that have already been generated and cannot foresee future content. This is like when drawing. You can only see what's already been drawn, unable to plan the overall layout in advance, resulting in generated images that may lack harmony in global structure. At the same time, the model can only predict one token at a time, unable to consider the correlation of multiple positions simultaneously. This is like when doing a jigsaw puzzle. You can only place one piece at a time, unable to consider the relationships between multiple pieces simultaneously, which may result in generated images that appear somewhat unnatural in certain details. However, researchers have noticed this issue and are exploring possible solutions. For example, by introducing more local interaction mechanisms or improving the prediction framework to better handle global information. What is the future development direction of Token Shuffle? First, researchers hope to explore its application in larger-scale models, such as 7B and 30B parameter models. Second, they are also considering how to support more flexible resolutions, and overall, Token Shuffle opens up new possibilities for autoregressive models in the field of image generation. It not only improves efficiency, but also enables the generation of high-resolution images. While there are still some challenges, its emergence undoubtedly brings new ideas and directions to the field of AI image generation. Alright, that's all for this video. If you're interested in Token Shuffle or other AI technologies, feel free to leave a comment below. See you next time.